So you write down the answer. It's easy to show that the Fourier transform of some signal times a cosine is going to be the spectrum of that signal delayed and advanced in frequency. And the amount of the frequency delay or advance is f sub c. Okay? And the half is there because we get the half from Euler's formula. So, and now we know what the Fourier series is, and we now can add the spectrum, and we get the following plot. So I like to use this example spectrum. It's called a rooftop spectrum because it sort of looks like a rooftop. And notice it has to be symmetric, right? What happens in positive frequency has to occur in negative frequency, and it has to be conjugate symmetric, which means for what I'm showing here, it's got to be an even function. We're going to use this a lot. So, the part that's due to the periodic part, those are those lines, like we always do, stem plots for things related to Fourier series, and the frequency at which they occur is minus fc and plus fc. For the non-periodic part, that's this, that's why you get this thing delayed and advanced in frequency, and the two add up. So you now, once you multiply by the cosine, you shift it up so the spectrum of the original signal now gets centered at f sub c. Okay. This is a very important example because this is amplitude modulation, and we're going to be very interested in how radio signals work. But we'll get to that a little bit later. Right now it's just an example for us exploring Fourier transforms. Okay, let's start filtering. I think it's pretty easy to see that the integral of a signal is just a sum. So we're summing up complex exponentials to create our signal x of t. So in terms of the spectra in the frequency domain, the Fourier transform of the output is just equal to the transfer function times the Fourier transform of the input. So to figure out how to filter a signal, like our friend the pulse, with our friend the RC low pass, what we're going to do is all we have to do is find the Fourier transform of our pulse, which we've already done. Transfer functions are already in the frequency domain in most cases. So we're going to figure out what x of f is going to be p, capital P of f. We're going to figure that out, multiply them together, and then we have to find the inverse transform of y of f to figure out what y of t is. That's the program. Okay, so we know what the spectrum is. I'm not going to write it in terms of the sinc function because there's a reason that you'll see in just a second. Okay, so we've already calculated the spectrum a little bit earlier, and now I'm going to multiply them together, and I think and this is the answer for the h times x is this complicated thing. So all we need to do is find its inverse Fourier transform. Okay, and so we just need to plug all that into there. I don't know about you, but I don't think that's going to be in an integral table anywhere. It's a little too complicated, and it's got lots of moving pieces. And again, I hate doing integrals. I'd rather use the properties if I can. This is what I normally do. I try to use the properties first, and if those fail, then I resort to doing integrals. You get a lot more insight into what's going on if you use the properties. I'm going to use this example to show you what I mean by that. So I'm just going to look at this expression for y of f in some detail. Well, some things ought to stand out for you. First of all, what's this do? So here we have some spectrum over here. When we multiply it by 1, we just get it back. What happens when we multiply it by e to the minus j2 pi f delta? You multiply the spectrum by e to the minus j2 pi f delta. What happens in the time domain? So, if we call this s of t, that's his inverse Fourier transform, this means time delay. And so this term in the time domain is going to be s of t minus delta. So all we have to figure out is what's the inverse transform of this term. Okay. To do that, I'm going to reorder things, just a little change to make it a little bit clearer. And what this looks like to me is I have some spectrum multiplied by 1 over j2 pi f. Well, that means integrate. What's this spectrum? Okay. I want to point out that one of the examples we did was this decaying exponential formula, and we found out that the Fourier transform of this was that. This is almost has the same form as that, and to get it in that form, I'm going to multiply and divide this by RC. And I think we can see now that A in the formula corresponds to 1 over RC. We have this 1 up top. I'm going to divide by, multiply by A. And that multiplies this side by A, again because the Fourier transform formulas are linear. If you multiply one by a constant, the other one gets multiplied by a constant. And so I know that the inverse Fourier transform of this term is this. And now we're almost done. Now I just have to, I know that the 1 over j2 pi f means integrate. So I just have to integrate this term. And again, this is an integral from minus infinity to t. It's always a definite interval. That's what integrate means. And so that's what you get when you perform the integral. And note that since the signal is 0 for t less than 0, so is its integral. Okay, everything at minus infinity is 0. Okay, and so we're almost done. We know that this term out here means delay. So the final answer is that. Looks a little complicated, but actually we've seen this already. Remember what happened when we took the periodic pulse train and sent it through our RC low-pass filter? I showed you some plots. I'm going to bring back one of those plots. So the input here, if you recall, was the periodic pulse train. So we had a pulse right there, and the period was 1 millisecond. And it was like that, and we got that for an answer. Well, I can think about this periodic pulse train as being a superposition of pulses delayed. Okay. So that means I can think of the output as being the superposition of these outputs. And so this formula should apply to that term. So let's just not ignore this part for a second, because that corresponds to this. And what we've done is put in a single pulse to figure out the answer. So now I have a much clearer understanding of how this signal is constructed, what its structure is. Okay, so let's go through it. The This starts at 0, and what it's going to do is go up and keep on going, and it has an asymptotic value of 1. Okay? The second term here, u of t minus delta. Notice everything here is delayed by delta, so this doesn't start until delta, and it's going to be the negative of what we have over here. Okay? So at delta, you get the same thing, headed toward minus 1. And when you add them up, you get this adds up, and then it turns out it goes down. It's going to go to 0 since plus 1 and minus 1 will cancel when you add them up. And that's what is going on in this waveform. So the shark fins that I referred to when we talked about the Fourier series, they actually consist of a rising exponential, 1 minus e minus t of RC, and then a decaying exponential. They are properties of the circuit, because RC only comes from the circuit. I should point out that the formula for a decaying exponential is frequently written like this, where that's a tau, and this is called the time constant of the exponential, just terminology. And so the time constant of these exponentials here is RC. Just a little fact, and so units of R times C, by the way, are time, which is kind of interesting. Okay, so this shows you how at least I calculate the output of a linear filter to any signal coming in. I find the Fourier transform of the signal, and then try to use the properties of the integrals, properties rather of the Fourier transform, to figure out what's going on. So we have finally finished our story of signals in the frequency domain. So if you have a periodic signal, its spectrum is given by a Fourier series. If you have a non-periodic signal, it's the Fourier transform and its inverse Fourier transform that describe how you go back and forth. We now know how to filter anything in the frequency domain. If it's periodic, we use the Fourier series version of things, and if it's not periodic, we use the Fourier transform version of things. I would always decompose a signal into its periodic and non-periodic parts, and then filter each separately, and then add the results back in. Superposition we use over and over and over again. It's very important. Well, we now know a lot about how to think about signals. We can think about their structure in the time domain. We can think about their structure in the frequency domain. Our next video is going to talk about speech. And we'll talk about the structure of speech and how it has both time domain and frequency domain parts. Really kind of interesting and fun.